Okay, so get started. So we're going to talk about the message passing interface, or MPI. MPI is probably one of the most popular, if not the most popular, scientific parallel programming method in existence. Um, it has a couple of unique features in that you don't have to worry about things like network, what type of network you're on, address of hosts, things like that. It kind of takes care of it all for you. It also gives a lot of abstractions to make certain types of communication easier. It is a distributed memory programming model it lets you use multiple computers for a single parallel run. So that is like if I had two laptops, each with two cores, I could run on 4 cores using MPI, and it would communicate between the machines, not just between the two cores inside a single machine. That's opposed to shared memory programming models like OpenMP or pthreads or Java threads, where all those different threads have to live inside a single machine. So if I had 20 laptops, each with 2 cores, I could never use more than two. I could run 20 copies, each running 2 threads, but that's the best I could do. With MPI, I could actually run a 40 processor single thing where all the machines would communicate between each other. One of the other benefits of MPI is it is a standard. It is not tied to any specific vendor's hardware. On Linux, there's many different versions because Linux is the most popular high-performance computing platform in existence. But there are versions of MPI for Windows. The Mac comes with one, and there's a lot of free and open source implementations of MPI you can download and build. Nice thing about that is, since it is a standard, you can use anybody's MPI library. You could be on a Cray where they have a highly optimized for their proprietary network, but you could have written a code on your Mac using MPI and then run it on the Cray using their MPI library, and it would just work. This is one of the nice things. There's a question, should we be seeing video? No, there's no video quite yet. I'll pop that up here in just a little bit. Actually, I'm going to do it right now. So this is, again, our YouTube channel where everything is already uploaded in terms of previous webinars we've had down here, as well as other video tutorials we have on how to do things. So MPI is a standard. There's something called the MPI form where the explicit definition of how MPI works is actually defined, but that means there's multiple implementations of MPI. The one we use on Flux most commonly is called OpenMPI. But something written to use OpenMPI will work with MPICH, will work with MVAPICH, it will work with MPT on a Cray, it will work with the IBM MPI. The standard when you write your code is consistent. So all you need to do is take your source code to another machine, recompile with their MPI library that's optimized for their network, and you're good to go. I'm going to be speaking a lot from an old document I have that is available on the cac.engine.umich.edu website under training courses. And you can actually get the example code we're going to use in this tarball down here. And there is a PDF of the slides I'm going to be working from today. So let's get into a little bit of the detail. So what is MPI? So you should be seeing video now. Want to make sure everyone is seeing video just fine. Okay, so what is MPI? It's a library that implements message passing, that is passing data between parallel processing units. It has C, C++, Fortran, and Fortran 90 bindings. So your language of choice is pretty much supported. For other languages like Python, R, Java, there are MPI implementations for them. Normally they live on top of one of the official MPIs, that's C or Fortran. So C and Fortran will pretty much always work, but you can pretty much always get a library like MPI for Pi, build it against their C MPI library, and now you can use MPI from Python. It's a series of functions that you call: send data, receive data, broadcast data. And some of the examples here, we're actually going to be doing them on Flux login. So here's a couple of links in terms of extra information you can look up about the MPI. Okay, So here's what an MPI program actually looks like. What we have is we have a program that runs, and we actually have 4 different executables running at the same time. You actually only write one executable most of the time, and they distinguish between themselves by something called their rank. So you see rank 0, which is on one core, rank 1, which is on another core, rank 2, which is on another core. And these could be 4 cores inside a single computer. These could be 1 core on 4 computers. It doesn't matter. And we call these different MPI functions like broadcast. In this case, rank 0 is going to send data to all the other CPUs, all the other ranks. Gather is the inverse. Everybody has a little bit of the data, and we accumulate it on a single CPU. And you have like normal pieces of simple send receives that send data between 2 processors. So that's distributed memory. So notice each one of these processes kind of runs independently through time, and they communicate between each other. If I look down here, this is an example of OpenMP, which is shared memory. So you kind of have like a master thread that you get to like a parallel loop, like a for loop, and you unroll it. And so you get these threads spawned off, and they've joined back together. So that's kind of one of the main differences. MPI is distributed, OpenMP is shared, in that you could have one thread doing a bunch of things, and then you could spawn off a bunch of threads to work on a parallel portion and then continue. This is easy to kind of get going right away with. Maybe modifying a serial code, but you're going to have a couple limitations. It's harder to scale bigger than a single computer. Like on Flux, the biggest regular node we have is 16 cores. The biggest non-regular node we have has 40 core. So, but you could never go bigger than that. While with MPI, I mean, there's machines, people regularly run multiple hundred processors on Flux, and I have a couple of users on Exceed and others that run thousands of processors using MPI. And getting the equivalent program in OpenMP to scale to that scale is very difficult, and the hardware to do it is even more expensive and difficult to come by. MPI can run on just regular servers with an Ethernet network between them, though for any performance you want to get something like InfiniBand. That's a faster network. But the point is you can buy pretty much commodity, regular, old, compute servers and get done what you need to get done. With shared memory programming, it's a lot harder. You have to buy these special supercomputers that actually are single large computers. Okay, so there are other alternatives out there to MPI. There is something that was called high performance Fortran, which didn't get very far. So in current times, it's probably better off to use OpenMP or MPI. Pthreads. Pthreads is very commonly used in the scientific world. Pthreads is a share in not the scientific world, in the computing world. Things like web servers and stuff will all use Pthreads. Realistically, for most scientific programs, unless you're a computer science mathematician type person, stick with OpenMP, which is normally underneath the covers implemented in Pthreads, but OpenMP will be a lot simpler because all you do is you get to a parallel loop and you say, hey, unroll this loop. With Pthreads, you have to be a lot more explicit with spawning the threads and bookkeeping them. With OpenMP, you don't have to. So I would recommend using OpenMP rather than using Pthreads. PVM, Parallel Virtual Machine, it's dead. It's actually really hard for me to get it installed anymore, so I actually don't support it on Flux. For that same functionality, use MPI. That kind of won out the culture war there. There is something called CoRay. CoRay is actually making a comeback. It's actually part of the Fortran 2008 standard, I believe. It's not well supported yet. On Cray machines and SGI machines, you can get CoRay pretty easily, and you can get PGAS, a PGAS library from Pacific Northwest National Laboratory to be able to implement CoRay. But honestly, it's not too well. If the CoRay model maps to your application very nicely, go ahead and use it. That extra effort of getting it to work at all on your platform might be worth it. But realistically, if it's only marginally different between that and MPI, stick with MPI. In fact, most CoRay implementations use MPI underneath, but they let you think in this distributed array type manner. SHMEM or shared memory type systems that were available with Cray and SGI, you probably want to use the MPI one-sided operations get and put, which we're not going to cover in this section because it's not that commonly used. Okay, so MPI, like I said, it lets you run between multiple computers, so the network between the computers matters for performance. Yes, you can run this as regular. In theory, you could run this over the internet. You could run it over your 3 megabit home DSL connection, but you're not going to get good performance. Because what happens a lot is when you're communicating with MPI, your CPUs are waiting for data to arrive before they can compute, so they're idle. I would never use less than 1 gigabit Ethernet, which pretty much any computer these days comes with. My laptop I'm on right now has 1 gigabit Ethernet. But your bandwidth is 1 gigabit, which is about 120 megabytes per second. And your latency, if you have a good switch, is going to be around 40 microseconds. While a gamer online would really like 40 microseconds, the realisticness is you're going to want faster than that, especially for scaling to a large number of processors and a large number of machines. A lot of the MPI libraries actually have optimizations for using shared memory. So this would be communicating between cores inside the same computer. So even though MPI lets you talk outside the box, you a lot of times have multiple cores inside the box. Like the nodes we're buying now for Flux have 16 cores. Just got announced that the future ones are probably going to be 24 cores. So there's a lot of cores inside the box. So you're going to use MPI to communicate between them. If you write specifically for shared memory, which MPI will do automatically, this is what's nice about MPI. It abstracts all this away. You don't have to worry about this. If the cores that need to communicate are inside one computer, it will automatically use shared memory. And as you can see here, the bandwidth varies significantly depending on the platform, but the latency is anywhere from 200 nanoseconds to a microsecond. So that's 40 times faster at least than going over the gigabit Ethernet for the latency. Latency is actually really important. That's the time it takes for the first bit to get there. Especially if you need to send small bits of information, the latency is extremely important. The bandwidth will matter too, because that tells you how long it's going to take you to get all the bits there. So then it turns out that in the outside world, in the HPC world, there's a lot of other networks besides just regular Ethernet and shared memory. What we have on Flux is what's called quad data rate InfiniBand. It's 40 gigabit per second, around 1.5 microsecond latency. There's other ones out there like Miracom, which is very competitive to InfiniBand. You generally won't find these in people's houses because they tend to cost $1,000 a machine, but they'll give you significantly better performance for your parallel application. Also, like on Flux, we also move data over the InfiniBand, so your access to disk is about 10 times faster than it is over Ethernet for disk. There's other limitations why it's not 40 times faster. And your home Comcast connection is 0.006 gigabit or 6 megabit. So that is an idea that every Flux node has 40,000 megabits of network and extremely low latency. But again, MPI is nice in that you write MPI and your cluster provider, whether it's Kane HPC, Exceed, Department of Energy, their admins will have installed an MPI library that will work with your code that will automatically take advantage of the optimized network on their system. And you can get the free ones that work on your own machine that use Ethernet. And so you don't have to write sockets for TCP. You don't have to write shared memory segments for shared memory. You don't have to do all these things. You just say send between A and B. So MPI abstracts all that away for you, so you don't have to worry about this, and it will automatically optimize. Are there any questions about that before I go into actually what's going on? Andrew, you're asking if you can specifically request a 16-core node on Flux. Yes. In fact, you could ask for no more than 8 cores in a node. No, actually, I think there are some 8-core nodes left, but I think there's only like 8 of them, and there's like 500 machines on Flux. So most of the machines right now have 12-core. They're dual socket 6-core, so 12 total cores in a node. Currently, there's 2,000 cores of 16 cores, so that's like 100 some machines. We're ordering 2,000 more cores of 16 cores. So then there'll be 4,000 cores worth of machines with 16 cores each. And there'll be 6,000 to 12 cores. And very soon here, the first 2,000 cores of Flux are actually going to expire and be replaced with 16-core nodes. So within 12 months, 6,000 cores on Flux will be all in 16-core chunks. And then the only 4,000 will be 12 cores. So, and definitely in the next couple of months, there will be no 8-core machines on Flux. They will all be 12 or 16 cores. Hopefully that answers your question. Okay, so MPI mechanics. So there's multiple parts to the MPI message, or what's called kind of the envelope. It includes the address of the data you are sending or receiving, the data type, the number of data types you're sending, and a tag to uniquely identify between two messages coming from the same location, a communicator, which I'll get into specifically later for collectives, and the rank of the target, so that is like where you're sending the data to or where you're receiving data from. So let's look at the very first functions you need for MPI. So I'm going to have the C and Fortran examples for everything, but the basic ideas are going to exist in even if you have the Python bindings for MPI. So the very first functions you need are MPI init and MPI finalize. They're to be only called once, and you need to call these before, you need to call MPI init before you do any other MPI call. So basically you have, if you have a C code and you have int main, then the next thing you're going to have is MPI init. And then right before your program ends, you have MPI finalize. If you're doing Fortran, right after you do, program definition, you define all your variables, you say MPI init, and then you do the rest of your code. And then right before your program ends, you have end program, put MPI finalize, and then end program. And so those are all subroutines in Fortran. So basically you need to call those first and last before you do anything. The next two functions you need to know are basically helper functions. These don't do communication, but they're to help you out. So there's two functions, MPI com size. And what that function does is it tells you how many processors you started up on, or how many ranks. So if I started on 4 cores, a 4 processor MPI job, MPI com size would put into the pointer size the number 4. Same thing with Fortran, the integer size would end up with the value of 4. And so I don't have to hard code any values of how many processors I'm using. All I do is start a different number, and I'll show you how to launch an MPI code in a little bit, because it's not the same as starting a serial code or a threaded code. But this is how you'll find out how many processors you started on. The next one is com rank, and this is the first time when you run your code that, remember that picture where I had the lines showing, and these lines are, each one of them the processor running their own executable. If I started the same executable on 4 processors, before running, the very first line of code that does something different is MPI com rank. And so what's going to happen is rank 0, when it calls this function, is going to get given 0. Rank 1 is going to be given 1. Rank 2 is given 3. And so this is now how I can distinguish between which processor I am, and thus I can divvy up work between them based on what number. Okay, so communicators and tags. So communicators specify a group of processors that can communicate together. This will become very important when we talk about collectives. There's a default communicator that's created. You can make your own. You can duplicate communicators, you can split communicators, you can even make communicators that communicate between communicators, which is kind of weird. But most of the time, all you need is MPI com world, and all that does is it's a communicator that includes all the processors that you started with. And so that's created at startup, and it has all your processors. Tags adds a distinct meaning. They're just an integer. And so you can use tags to distinguish between two messages between the same processor, so you know what's supposed to be received where, because messages may be received out of order. They're very useful for kind of distinguishing what's going on. Data types. MPI defines its own, but they pretty much all map to a traditional Fortran or C data type. So you have chars, ints, floats, and doubles. So here's the very first basic communication function, MPI send. So MPI send tells a processor that calls it to send data to some other processor. So let's look at the arguments here based on what we know. So we have this buffer. This is a pointer that points to the data you want to send. So if I have an array A, I would put A here. We have the count, which is the number of elements of A I want to send. We have the data type, which is going to be that MPI, float, MPI double. So that basically says how big the type in my buffer is. Then I have the destination rank. Whoops. And so this is an int. So this is the rank of the processor I'm sending to. So if I'm processor 0 and I want this to go to 2, I would put int 2 there. And then the tag, again, that is just to be your own descriptive piece of information so that you know who if I sent to the same processor twice, 2 different pieces of information, I know which one's which. And then this is the communicator. So by default, put in MPI com world, but you can have other ones. The Fortran prototype's basically the same. The difference being that there's an extra argument for the error. The C function returns a success code or not. Fortran, since it's a subroutine, it takes this extra argument error, so you can check to see whether or not there was an error during the send. So the send basically sends data to one or the other. So let's look at this envelope stuff more closely. Why is that not showing up? Sorry, I'm trying to share something with you guys and it's not showing up for some reason. Why is it not showing up? Okay, well here I can try this one and maybe I can use this. So remember we have a if I have an array, oops. If I have an array A, and it contains multiple, say it has 4 doubles and they're doubles. So I have to have the buff, then I have the type, and then I have the count. So what does that work out to be? I know the type's a double. The buffer I know is A, which is some address in memory, and I have the count, and I know it's 4. So what does this really say is doing it? It says that starting at the address where the array A lives, doubles, which happen to be a certain size, which on our system is 8 bytes, and I have 4 of them. I need to, this MPI send now knows that to starting at this address, send 8 times 4 bytes of information starting this address. So basically it'll copy from there to there automatically. But it lets you think in terms of number of doubles or number of structures or number of chars or things like that. And so that's how the envelope works. Address in memory where the array or data type are, how big are the individual elements, and then how many elements to send. So that's how that works. So that's why we have to have all these different types in there. And then the tag and destination, it's where to send it, what communication was it, and then the communicator really goes along with the destination because a processor may be part of multiple communicators and its rank inside each communicator may be different. But think right now in terms of only one. So for every send, there must be a receive. So remember, we're sending between processes that are running independently of each other. So it's not magically written into the memory of the other. So for every send, remember how on the send, there's this, who I'm sending it to? Well, on that processor, I need to call receive. That basically has the same piece of information, the buffer. In this case, it's the buffer that I'm going to write into. So it's an array that I already have, but I'm going to overwrite the data in it. Number of things I expect to write. this number can actually be bigger than the number you actually receive. I'll show you how to be able to find out how many you actually receive. The type you expect, so like a double, who's it coming from, so who's doing the send, the tag, and the communicator, and then this special status struct. So to have a communication happen between a send and a receive, the source, tag, and communicator must all match, or the communication doesn't happen, and it just hangs. Other things here don't necessarily have to match, but if they don't, you may get corrupted information. So, you want, of course, the buffer to be big enough to hold at least the amount of data coming, and you want to have it say that you expect at least this many to come. Where I said that this doesn't necessarily have to be the exactly the right size. The status structure that goes here you can interrogate this to find out who actually sent it, and how many were actually sent. Because there is, for this source, there's a special option you can put in called MPI any source, so that this receive will accept data from any processor, no matter who it is. There's also an MPI any tag, which will accept data from, a matching source that has any tag, and then the status object again will have you tell you what the real tag is, how many pieces of data were actually received, and who the actual sender was. Fortran is identical, except again it's got the extra error function because it's a subroutine. Can't return an error code. Okay, so I'm going to go ahead and run some example code. You can download this out of my home directory on Flux, but I'm going to go ahead and run it here. But before I do any examples, do we have any questions? Okay, it doesn't look like we have any questions, so I'm going to go ahead and grab. Okay, so here I am on Flux. See, I'm on Flux login. So I've got this example code, and the example code I have is hello world. I'm going to look at the C version. And so to get started, what I have to do is I have some includes that are just in your normal C includes, but one of the main includes that I need to use MPI is mpi.h. This is the MPI library header file, and thus gives you all your functions. So this is a simple hello world program, but it's going to demonstrate, a init, finalize, com size, com rank, and send and receive. And so let's look at this. So here I have main, where the application starts. Now I have a couple of variables defined. So I have rank, numprox, tag, which is set to 10, a message I'm going to be sending, and an MPI status object. And so now my main application actually starts. So the first thing I do is I call MPI init. Remember, I have to call init before I can do anything else, and I can only call init once. Then I call com size, which tells me how many processors I started up on. So the variable numprox is going to have the number of processors I'm running on. And then I call com rank. And so rank on each processor is going to end up with a different value. So if I ran this on 4 processors, there's going to be 4 copies of this code running, each with their own unique variable, rank, numprox, tag, and message. Remember, distributed memory. There's going to be multiple copies of this running. And thus, this function really gets called 4 times, and there's 4 copies of rank, each with their own values. So you can see here, I have this if statement. If my rank is not 0, so every processor except for the first one, because the processors are numbered 0 through n-1. If I'm not 0, I say receive, and I'm going to write the results to the integer message. The number of things I expect to receive, which is 1. The type I expect to receive, which is an int, so I'm using MPI int, and that matches the type of the buffer I'm writing into. Who I'm receiving from, in this case I'm receiving from rank 0 in the communicator. The tag that I expect, I have set to tag, which is set to 10. The communicator, which is MPI com world. And then I have the status object, which is just this MPI status object. So what happens is MPI was called blocking. So when I get to this receive, I sit here until this message is received, and then once it's received, I continue on with my code, which is print out hello from process, and I print out which rank I am. So this is wrapped in an if block, so this only happens if my processor rank is not 0. So this is going to be 3 of my 4 processors. The first one's going to do something different though, and that's caught in this else block. So if you're not processor 0, you receive. If you are processor 0, you send. And so what processor 0 does, it prints out MPI com world is this processor's big. So I print out numprox, which was filled in from MPI com size. And then I loop over all the processors I have, which is numprox, and I send to them. So I send number to send. So I'm sending X, which is defined here. 1 int, so count is 1, MPI int. Rank to send to, which is X, so I'm going to loop over. So I'm going to send to every rank. Then the tag, which is sent to 10, and MPI com world. So things can be static or they can be variables. There's actually a better function than this, than looping over all the processors with a send. This could easily be done with a scatter, an MPI scatter, which I'll show later. So in one line, I can do exactly what I did. And so then when the code's done, I call MPI finalize and return 0, and then I'm done. So that's your first MPI code. So how do I compile this? I use MPI CC, which is a wrapper compiler. And then I just use normal code. So this compiles the code, which in our case is still using the Intel C compiler underneath and links with the needed MPI library. So this gives me an executable called hello C that's got all my MPI libraries attached to it. But to run it, I have to use something called MPI run. If you're running on Flux and you're running under PBS, you would just do hello run, MPI run the executable. And our MPI run knows how to find out how many processors you requested. But because we're testing here just on a login node, I need to specify the number of processors using MPI run NP4. And so this says start up this program 4 times. So I run it. And so you remember that if statement where it said, hey, if I'm processor 0, print out the number of processors in this. So it's 4. And all the other processors print out the hello from process. Notice the order here. The order is non-deterministic. If I run this again, okay, I'm going to get it in order, but notice that they're out of order. So here, 1, 2, 3, before I had 2, 3, 1. So the order you print from the different processors doesn't follow any order. It's whoever gets there first, and they don't necessarily go in the same order. So if I ran this on 8 processors, because I'm using MPI com size, MPI com rank, my code automatically scales to 8 processors automatically without me having to modify anything or recompile it. Any questions? Okay, so hopefully that gave you an idea of what how MPI's basics kind of are. That'll give you an idea that there's multiple processes out there running, and that they actually, they pass data between themselves, and so data actually are allocated multiple times. So there's something called deadlocks. Remember how I said that MPI receive will hang until it gets the message it needs? So you can get into these situations where you have like 2 processors trying to send to each other at the same time, and they're waiting. For the other one to receive, and so they basically get stuck. So every MPI send must have a matching receive. A call that does not have a matching send or receive is deadlocked. Calls do not return unless the buffer is safe to reuse, not that the data was received. That's a subtle thing. Normally, it doesn't actually matter, but it is the case that just because a call returned with normal MPI send or receive, it just means that you're safe to overwrite the data in the one. You can't assume that the receiving processor actually has the data yet, because the network stack might copy it into a buffer space or something like that. Some MPI libraries will let deadlock code run until it reaches a certain size. I actually have a demonstration of this. This has to do with some optimizations that some MPI libraries do. But I'll show you what can happen. Actually, I think I have an illustration first. So let me show you the illustration first. So this is what's going to happen in a deadlock example. I'm going to run on 4 processors, and every processor is going to try to send to 1 to its right simultaneously. And so 0 is going to be try sending to 1, but 1's not going to receive it because it's trying to send to 2, and 2's not going to receive from 1 because it's trying to send to 3, but 3, and so you kind of get stuck. Because this is doing send, then receive, this is doing send, then receive, send, then receive, send, then receive. And so they never get to their receives because they're all waiting for the other one next to them to receive, but they're all trying to send. So they're pretty much stuck. At small data sizes, though, a lot of MPI libraries will do this optimization where if the data are small enough, it will copy into a temporary buffer and let your program continue. But once the data are bigger than some amount, it no longer does a temporary buffer because it doesn't want to spend the memory on it, and it assumes that for the data size, the network's slow compared to memory allocation. So here's what it looks like. I have the exact same code, but I'm going to send a different quantity of data. So I have this code called deadlock, and I'm going to run it on 4 processors. And so what happens is it's trying to send 504 doubles of an array to the next processor, and it's just stuck there. It's just hanging. It doesn't finish. So I'm going to kill that with Control C. But that exact same code sending 503 finishes almost instantaneously. And the reason is because I know that 503 to 504 is crossing that threshold. This threshold is tunable, so if you have no more memory, talk to your cluster admin, because you might get better performance if you can keep this overlapping communication going with computation. But if you don't have enough memory, it's better to not have deadlocks. That is, interleave your sends and receives, so that you don't have this kind of problem happen. But what will happen is you'll write a code, it looks like it runs fine at the small scale, and then when you run it at the larger scale, it locks up. And the reason it locks up is because of this problem. When you were debugging it on the small case, it worked, but at the large scale, when it was sending larger chunks of memory, it just hangs. One of the ways you can get around this with send and receive, if you need to do something like this, is to use a function like send receive, which sends and receives simultaneously from 2 different can send to one processor and receive from a different processor in one function call. And so this is much simpler than trying to do the intermixed with like every odd processor receiving first, then sending, and every even sending and then receiving. So this can save you a lot of work, and plus then it's only 1 line instead of like 5 lines with an if statement. There's also something called non-blocking functions which you can use. So these start with an I, so there's MPI I send and MPI I receive. You can mix blocking and non-blocking. That is, you can have an MPI I send to an MPI receive, and vice versa. The thing with asynchronous calls are that they do not block, but that does not mean it is safe to reuse the buffer, unlike with the blocking cases. They have an extra argument they take that you can run MPI test or MPI await on them and refer to the MPI documentation for this, which will tell you whether or not the communications actually happened to the point where you can overwrite that data in your original sending buffer, or to say that you've actually received it and you can actually read data out of that buffer. Okay, collectives. Collectives help your life out significantly. These are operations that work on an entire group of processors, and those groups are defined by those communicators. So now instead of saying send to processor 0, I say broadcast to MPI com world, so send this to everybody. Remember I said you can define other communicators of different number of processors and different processor members and stuff like that. And so you can do broadcasts and stuff to other bits. But here's some of the most common set of collectives. There's barrier, which is kind of for synchronizing. All the processors wait until they all get to the barrier. Broadcast, send data from one rank to all others. So if you have like say a coefficient that you need to broadcast to everybody, you can do that by using a broadcast. MPI reduce, do an operation data on all processors and store the result in a single rank. This is handy if you want to do something like an integration. I'm going to have an example of that where every processor has some fraction of the data and you want to sum it all up for a global sum. You can use reduce for that in one step. Rather than sending all the data back to one processor and then doing the math, there's actually an MPI function that does all that for you. Scatter, if you have an array of data and you want to break it up and send pieces of it to all the different processors, you can do that with scatter. Gather is the inverse. That is, every processor has some of the data and you want to accumulate it, not in a sum like in reduce, but in one big array. So the arguments for something like broadcast is a little bit different. I have the buffer that I'm sending, and I have the number of things I'm sending into type, and then the root and the communicator. So the root is who's doing the sending. So the buffer on the root rank is what I'm sending. The buffer on the non-root rank is where I'm going to write the result from the root process. And I'll demonstrate this. So the buffer, when you call this function, is both sending and receiving. It's sending on one processor and it's receiving on all the others. So reduce, this is the one that accumulates data. So it's got a sending buffer. This is the partial data that you want to sum up everywhere, for example. Receiving buffer is where you're going to write the result. And again, the count is the number of pieces of data everybody's sending. The data type, is it a double? The operation, and I keep saying sum, but there's other ones you can do bitwise operations and such. Root, in this case, is who you want to store this on. So receive buffer must exist on all the processors, but only receive buffer on the root processor is going to end up with the result. And then the communicator is representing the group of processors taking part. Here's all the default defined operators for reduce. So there's max, min, product, sum. So if you want to find a global max across all these processors and store it on one, you do MPI reduce, the data, and then the max. Min, product, sum, logical and, logical or, logical exclusive or, bitwise and, bitwise or, bitwise exclusive or logicals. So here's an example. I'm going to calculate pi by doing numerical integration of the function 4 over 1 plus x squared from 0 to 1. So this is known to be an approximation to pi, and so I'm going to do this by breaking. I'm going to evaluate this function at endpoints and do the midpoint method. I'm going to actually calculate the area of those rectangles and sum them up. So what's nice about this is what I can do is I have each CPU work on a subset of them. So if I had 4 processors and I was doing 4 rectangles, each of them would calculate 1 rectangle. So this is going to demonstrate reduction because every processor is going to have 1/4 of the area under the curve. So I need to sum it up. So I'm going to use reduce for that. I'm also going to take an input that gets brought on one processor that gets broadcasted to all the others. So here, let's take a look at the actual code. Ken, you were asking about the example. Sorry, I didn't see your question. If that example, I guess you're referring to the deadlock, if that ran on 1 core or 4 machines. It ran on 4 cores on 1 machine. The machine I ran it on, the Flux login node, has 12 cores. So it ran on 4 cores on 1 machine, but it could very easily have been 1 core on 4 machines or 2 cores on 2 machines. It was just 4, and you have to know how to lay them out, which if you're using the batch system on Flux or some other cluster, it automatically does that for you. Okay, but let's look at this calculate pi example. Okay, so this is a Fortran example. When using Fortran for MPI, you need to use this use MPI statement, and this gives you all your MPI functions. But everything looks kind of like what we saw before. We just still have normal data types of things like rank, number of procs, error. But I've got a lot of doubles here. So here I do the usual. I do MPI init. Before I can do anything, I call com rank to get which processor I am. I call com size to find out how many processors there are. And then I say if my rank is equal to 0, then print out the number of processors in com world. And then I actually prompt for some input. For a batch program on an HPC system, this is not a good way to do this, but this is just for demonstration purposes. So in this case, the first CPU is going to ask for some input. Then, notice there's no if statement wrapped around this broadcast. That means every processor is running this function. But I do a broadcast of n to n on all the processors. So n, amount of data to send, count, which is 1, is a double. I'm sending from 0 to all the other processors. So n, notice I read in n here on processor 0. N exists on all the processors, but it only exists with a real value in it on 0. So in this case, n is sending from 0, and n on all the non-zeros are now being written into from the value of n on CPU 0. And that's all CPUs in COM-world. Then, if you notice here, here's the actual math. So let's look at the logic here a little bit. The width, I'm integrating from 0 to 1. So the width of my rectangle is 1 divided by the number of rectangles I'm breaking it into. What I'm doing is I'm going to loop over what rank I am to n, stepping by the number of processors. So CPU 0 is going to do a rank 0. If I ran on 4 processors, it would be 0, 4, 8, 12, 16. 1 would be 1, 5, 9, etc. 2 would be 2, 6, 11. See, so every element of the rectangle is actually being covered, but I'm striding by the number of processors, and they all start at the number of processors. Let's see, everybody's doing this. So everybody has their own local area that I'm accumulating in. So I have 4 areas, one on each processor, where they've each stepped through their own 1/4 of the rectangles in my area. So I have this local sum, you could say, on each processor. So now I want a global sum. So what I do is I use MPI reduce, and I'm sending area, because this is everybody's fractional. I'm going to store in total the one double, and I'm going to sum it. I'm going to store the result on CPU 0. So the variable total on CPU 0 is going to end up with the total area from the partial sums. And it's MPI com world. And so then if my rank is 0, I have to do some normalization, but then I just write out the value of total. Then MPI finalize and end program. So any questions about the source code before we continue? Okay, I'm going to go ahead and run it. And so this is what it looks like. 4 processors, fpi. CPU 0 is going to ask me for the number of rectangles, so let's do 1,000, and it calculates pi. Okay, so let's do this on... I'm going to do a little trick here. Unfortunately, computers are getting too fast these days. I can't actually demonstrate this. Okay, so on 4 processors, this is going to take 41 seconds. If I run this on, say, 8 processors, same number of rectangles, it still took 41 seconds. That's screwy. I must be running into some sort of other overhead here. But yeah, okay, so I'm running into something else here because it's kind of a contrived example. But in theory, I have 8 processors. They're each working on 1/8 of the total, and the total stayed the same, so it should go faster. Okay, so let's move along. So that's collectives. Notice I didn't have to do ifs and stuff, and everybody got to communicate in one line instead of having to do a bunch of looping over the processors and such. So here's just some demonstrations of gather and scatter. So if I kind of write my data this way, I have data, 4 chunks of data, and they're all on CPU 0. After the scatter, on 4 CPUs, they each end up with 1/4 of the data. All gather, so gather is the exact opposite. All gather, on the other hand, is kind of like a gather followed by a broadcast. So gather would just change this into one array across on processor 0. All gather, and pretty much all of the collectives have an all equivalent. So there was reduce. So remember, MPI reduce stored the result on just one processor, whatever the root processor was. If you did an all reduce, all the processors end up with the result. And so this is like an all gather where if I have distributed data, everybody ends up with all the data. Collectives. These things though, if you can do an algorithm that doesn't use these, you're generally going to be better off. But if your algorithm is just faking this, like instead of doing all reduce, you do a reduce followed by a broadcast, that's functionally the same thing. And if that's the algorithm you need, use the all reduce function because it is more optimized than reduce followed by a broadcast. It can do more intelligent things. So getting into some more advanced topics, there's something called MPI Cartesian Create, which creates a communicator, kind of like MPI COM World. But remember, the communicator is just 0 through n-1. The MPI Cartesian Create lets you create a communicator that has Cartesian coordinates. And it can be periodic too, so that way you can do like cylindrical units just by saying that, hey, the x direction is periodic, so if I step over bounds, I just end up at the beginning. And what it does is it has a couple of functions, so you can give this communicator with, I want cell 2 where x equals 2 and y equals 3, and it will turn it into the corresponding CPU for all your other communications. There's some timing functions. They're helpful. But let's get into some documentation. So there is a class offered where some of this stuff is covered in more detail, which is EECS 587. It'll cover a lot more of the mathematics effort of how to parallelize something mathematically. The definitive text on basic MPI is the Grop, Lusk, and Seljam book. There are copies of this available online as well as in the library system here. I also really like this text, this parallel programming in C with MPI and OpenMP, and parallel scientific computing with C++ and MPI. Both of these look more like a textbook, so they give you enough MPI to solve some mathematical problem. And if you're more of a scientist and a programmer, those examples might make more sense to you. Though for self-directed learning, for like a tutorial, this CI tutor, which actually I got to update that link because it's now citutor.org, from National Center for Supercomputing Applications. They have a self-directed course on MPI and a more advanced one, as well as a bunch of information on like shared memory programming and other things to worry about. But their MPI course is very in-depth. It's self-directed, has good examples, and I really like it. It's definitely the one I prefer and where I point most people. So after this, I would recommend going to citutor.org and working your way through the examples by signing up for the introduction to MPI. Or if you've done some MPI before, go ahead and jump into intermediate MPI. But that's really everything I have. If you need to get a hold of us, remember it's hpc-support at umich.edu, which again I put in the chat box. But otherwise, that's everything I have. Please, put any questions you may have right now in the chat box, and I'll be sure to get it answered. Pratik, some basic tricks to improve parallel efficiency would be great. Okay. That's probably beyond the scope of this, and it really depends on what you're doing. There's all sorts of tricks, like if you're really latency bound, maybe it's better to do everything inside only one computer. Don't use an external network. Overlapping computation and communication by using asynchronous calls, batching up communication into bigger messages fewer larger messages rather than greater number of small messages. There's just a whole lot of different things. Also, we have a tool that gives you a lot of insight into your MPI code. Called MAP. There's no documentation really available for it yet, but if you search for it on our website, you can find the manual, and that'll give you a lot of input. So other than that, other questions? Anything you curious about or questions?